Alright guys, this is lesson 2.4. We're going to talk about something called U-Substitution. So the trick with U-Substitution is knowing when to do it and then also how to do it. So we have two things that we need to make sure you know how to do. How can you tell when to do U-Substitution for integration? And then after that, how do you do it? The steps on how you do it are pretty much always the same. The trick is just identifying when. So let's go ahead and take a look. So first of all, I want you guys to pause the video here, and I just want you to think for a minute about the answer to this question. All right, so so we had a derivative here, right? Now, I'll just tell you the answer. The original function would have been cosine of 4x squared minus 3. That's it. Now, how might have somebody gotten there? Well, when we look at this, hopefully from Unit 1, you guys are recognizing that we have an inside function here, right? And so we have an inside function and an outside function. Now, when we do a derivative, don't we, of a composite function like that, don't we usually multiply the derivative of the outside times the derivative of the inside? So this would represent the derivative of the outside, and this would represent the derivative of the inside. And sure enough, if you compare the 8x to this, what's the derivative of 4x squared minus 3? Well, it would be 8x, right? So this is just the derivative of the inside. Now, if I'm working backwards, then this is just going to go away because the inside just stays as the inside when you're working backwards. And all we really need to do is just figure out what's the integral of that. So what is the, well, you know, so we haven't really talked too much about the integrals of trig functions, but you guys know that, you know, if you're trying to work your way backwards, well, what function has a derivative of negative sign? And that's cosine. And we'll get to trig ones a little bit later, but still just working backwards from derivatives that we could have gotten there. And we can always have a plus c, that's a possibility. But there it is. So wanted to give you guys this opportunity to look at this because what I'm trying to do with this exercise here is get you guys to be able to recognize the first thing on our list of objectives is how do you know when to do this thing called U-substitution? Okay, well, this slide kind of helps you recognize it. Here it is. When you see a inside function, let me delete this. I wrote it actually. When you see an inside function, and whenever you see the derivative of the inside function. So when you see an inside function and a derivative of the inside function, that's whenever we're going to use this process called U-substitution. Now you guys don't even know what that is yet, and yet some of you probably got the answer. Well, that's because this one I made it simple enough to where you don't need a algebraic process to help you get the answer. You can really just kind of use what you know about derivatives to figure the answer out. But some problems are complicated enough to where just looking at it, you're not going to be able to get the answer. So we're going to go through a little bit of a process, okay? And it's called U-substitution. And what the U-substitution is, where we kind of ignore the inside function for a minute, and we just replace it with a U. Now, why do we pick U? There's no reason. We just pick U. It doesn't matter. You can use any letter, really. I wouldn't use the same letter that's already in the problem, like X. I would use something different, but just pick a letter, replace it, because what the goal with U-substitution is to take something that looks complicated and make it look a little bit less complicated so the integration becomes easier. Okay? Now, if this is U, then you know what this is? This is the derivative of U with respect to X, isn't it? That's the derivative of U with respect to X, right? Another way you can say it is U prime. It's the derivative of the inside. Okay? So this is my U, and this is the derivative of U with respect to X. Now, if I wanted to integrate this thing, with respect to x, like that, well, now I've got two dx's and they cancel. So really, I just want to find what's the integral of sine u. Right? I've just changed the variable I'm using, but it doesn't matter. And the answer is cosine, right? But remember, that u is not really a u. What was it? It was 4x squared minus 3. So that's probably a little bit overwhelming for you guys at the moment. I'm not too worried about you guys getting the whole concept just yet. I'm just explaining it to you. So what is U-substitution? U-substitution is a way to make a problem look less complicated. And what it is how do you know when to do it? You do it whenever you have an inside function and its derivative, and you're trying to integrate. Okay. So now you guys might have noticed at the beginning of our slide here, I had a chain that's being snapped. Why did I have that there? Well, because U-substitution is the opposite of the chain rule, right? So, for instance, if I have cosine of 4x squared plus, I don't remember what the number was, say plus 3, and I want to find the derivative of that, we do the derivative of the outside. Oops. Multiplied by the derivative of the inside. That's the chain rule. But if you want to work backwards and break the chain, that's U-substitution. Okay? So U-substitution is the way that you integrate a function or an integrand that was arrived at by doing a chain rule. And so once again, the way you recognize when to do U-substitution is by noticing that you have an inside function and its derivative in the integrand. So here we go. This is kind of your setup. This is honestly not all that helpful of a slide, but we can write it. It's just not very helpful. But whenever you have a function with an inside function and you see the derivative of that inside function, then we're going to be using U-substitution. And when we integrate that, the integral of f, this should actually just say f, not f prime. The integral of little f becomes big F. The derivative of the inside goes away, and we're just left with that and plus c. So, now don't worry, if you're still a little bit stuck on how to do this, that's okay. I'm not worried about that. We're going to get the steps down in a minute about how to do this. We're going to really drill it into, and you're going to get it by the end of the day, I promise. It's not that bad. The issue is I want you guys to make sure that you know when to do U-substitution. I'm going to say it again for the millionth time, just for fun. Okay? When you see an inside function and its derivative, that's when you do U-substitution. All right. So, this is just a reiteration of everything I've already been saying, so I'll skip that. All right. So there it is. So now I'm going to be giving you guys some steps to go through here for U-substitution. And we're going to spend 2 days on this lesson because U-substitution is actually probably one of the most common integration strategies you're going to use. It's one of the most common ones you're going to use. And so there's a ton of questions that go along with it. And so we want to expose you guys to as many different types of questions as possible. So let's go ahead and take a look at the basic. This is the most basic one I could think of here. So here we go. So first of all, how do I know this is a U-substitution problem? Because it is. How can we tell? Well, do you see an inside function? I do. That expression right there is inside some parentheses, so that's an inside function, right? Do I see the derivative of that inside function? Well, what's the derivative of 2x to the fourth? Well, that would be 8x cubed, and there it is. So I have an inside function, and I have its derivative. That is whenever we're going to do this process, which I'm about ready to walk you through. Now I'm going to be writing some steps off on the side here as we go. You don't need to write the steps because they're already at the end of your notes, but if you want to write them, because you like these steps better than the ones I give you at the end, you can. But here we go. So step 1 is to set the inside function equal to u. Okay? Now, before I actually go any further, I want you guys to realize my goal here is to completely get rid of the x's and replace everything with u's. But in the process, what's going to happen is it's going to make this thing, which looks kind of complicated, look a lot simpler. So that's the whole purpose of U-substitution, is it makes an integrand that looks complicated into something that looks simpler, so it's easier to integrate. That's the purpose of U-substitution. It's just a cosmetic, algebraic move. Cosmetic meaning to make it look prettier, algebraic meaning mathematical, right? So we're just doing a cosmetic, algebraic move to make it look easier to integrate. So that's why we're going to be replacing all these x's with u's. And the first step, as I've already said, is to replace not to replace, but to set the inside function equal to u. So let's do that. 2x to the 4th minus 3 equals u. Okay? So there's that. Now, what I want to do is I want to take the derivative of this thing with respect to x. Well, actually, I'm jumping into the second step now, aren't I? So, let me back up a little bit. I'm going to change my color. So step 2, find the derivative with respect to x. Find the derivative of this thing with respect to x. So the derivative with respect to x. Here we go. So if I take the derivative of that, I'm going to end up with 8x to the 3rd. The derivative of that is 0. And the derivative of that with respect to x is just going to be du dx. You could also say u prime, but I don't want to say u prime. Okay? Because you'll see why later, but when it comes to the integration process, we need this little thing in there. That matters. And so instead of using u prime, we're going to use du dx instead. But u prime would work. Okay? All right, so there's that. Now here's the next step. We want to get the dx by itself. So we want to solve for dx. So I want to get the dx all by itself. I want to solve for it algebraically. So here's what I'm going to do then. I'm going to multiply both sides by dx. And over here they cancel. So now I have 8x cubed dx equals du. But I don't have dx by itself yet, right? I want to get dx by itself. So my next thing I'm going to do is I'm going to divide both sides by 8x cubed. All right. So now to finish up step 3, I'm out of space, so I'm just going to put step 3 continued. We have dx is equal to du over 8x cubed. Okay. Now let's talk about this. What are we going to do now? Remember, my goal was I want to replace all of these x's up here with u's. And we can do that because now I've got something for all the x's that are up there. First of all, this whole thing I said is u, so I could just replace that whole thing with u. Next, I can get rid of this, the dx, because I know that dx is equal to this, and that's got a u in it. Now you might be a little bit bothered because you're thinking, well, there's an x here, so if I put that in there, you're just going to put another x in, but you're going to see something kind of cool happen in the process there. So follow along with me here, and you'll see where I'm getting at with this. So step 4 is to substitute the u and du. Okay? So what do I mean by that? We're going to replace the inside function there with a u. because 2x to the fourth minus 3 is u. So I'm just going to put that there. 3 can stay there. I'm going to replace the dx with this. There's only one thing I'm not going to replace, and it's this derivative of the inside there. But you know what? That's actually okay. And here's why it's okay. We have 8x cubed over 1, and we have 8x cubed on the bottom. They cancel each other out. And now I have something much simpler to integrate. So step 5 is to simplify or cancel the x's. Okay? So, there you have it. Now, you guys can agree that this is much easier to integrate than this would be. Okay? It looks a lot nicer anyway. And so the whole purpose of steps 1 through 5 is just to rewrite this thing so it looks easier to integrate. And we call that U-Substitution. And you do that anytime there's an inside function and its derivative. But we're not done with the problem, so don't get too excited. We still have to finish this problem. So the next step is to go ahead and integrate it. So let's do that. So if I want to integrate u with respect to u, and by the way, that's important that it says du here. We couldn't be integrating u with respect to x because they don't match. We can only integrate u with respect to u. So that's why this du thing matters here. So we're going to integrate this u with respect to u now. So that means we're going to add 1 to the power and divide by that value, and then we're going to add a c. All right? We're getting there. We are getting there. We have one more step. One more step. Step 7 is to replace the u. In other words, we put the u in there just so it would look prettier. But now that we're done with the problem, we actually need to put back what it was originally. So what does u actually equal? U actually equals this thing here. So I'm going to replace my u with 2x to the fourth minus 3. And there's my final answer. Now I'm done. Okay? But before I say I'm done, even though this is a good answer and this is 100%, there is another way you can write your answer. And I would encourage you guys to write down both, because otherwise you might not be able to find your answers on a multiple choice test because they could write their answers in different ways. So this is one way they might write the answer. The other way is by writing it with a fraction instead. So instead of putting it over 4, they might write it like this. So instead of making it a fraction where it's 2x to the fourth minus 3 over 4, they might just put 1/4 in the front of it, which is the same thing as putting it over 4. Okay? So there are two possible ways to write the answer, and I would encourage you to know how to write both. Okay? Now that's the process. You guys are probably thinking, man, that's a lot of steps. It is, but here's the good news. The steps pretty much stay the same. They don't really change throughout the entirety of the process. So we're going to have those same 7 steps. So steps 1 through 5, what are they? Steps 1 through 5 are to get rid of all the x's and replace them with u's. Okay? So set the inside function equal to u, find the derivative, solve for dx, replace everything that you can. You're going to substitute what you got for u in, and you're going to substitute what you got for the du in. After that, you're usually going to be able to simplify it a little bit. After step 5, you should have no more x's in your problem. After that, you just integrate, and then when you're all done with that, replace the u again with the x's once again. Okay? So it's the same steps. And those are the steps on how to do U-Substitution. But once again, how do you know when to do U-Substitution? when you see an inside function and its derivative. If you don't see its derivative out here, then U-substitution is not going to work, because remember how we had the du over 8x cubed? Well, if you don't see this thing out here, then these aren't going to cancel, and you're still going to have x's, and it's going to create problems. So you need to see the inside function and its derivative. So a lot of information, but that's okay. We're going to do a guided practice. So we're going to walk our way slowly through this. All right, so step one, go ahead and see if you guys can do just step one. Just step one. There's not a whole lot to do with it. Just go ahead and try to do it. Pause the video here and give it a shot. All right, so step one, you guys should have done this. You should have taken the inside function and set it equal to u. All right, that was step one. Step two. Go ahead and pause the video here and do step two. Step two is to take the derivative of this thing with respect to x. So the derivative of u with respect to x is u prime, but we're not going to say prime. We're going to use this notation for a derivative. And now you guys see why, because we need that in there, right? Instead of a prime, we use du dx. And now we take the derivative of that, so that should have went away, and then we take the derivative of that, and we get 15x to the fourth. All right, go ahead and do step three. Pause the video and try to do step three. Step three was to get dx by itself. So the first thing you should have done is multiplied the dx on both sides. And then you should have divided the 15x to the fourth on both sides. And if you do that, you would have ended up with this. Okay. Step four. Go ahead and do step four. Pause the video. This is the U-substitution step. So for step four, this is what you guys should have done. You should have replaced the inside function with what it equals, u. The 15x to the fourth is going to stay there for now, but the inside function is going to get replaced with a u. So instead of 3x to the fifth minus 2 raised to the fifth power, it's just going to be u to the fifth power. And you also should have replaced the dx. We know that dx is equal to that. All right. Now go ahead and do step five. Step five is pretty chill. All you do is these cancel. And like we said, at this point, by the end of step five, you should have no more x's. It should all be u's. All right, go ahead and do step six. Step six is your integration step. So for this step, we're going to add 1 to the power. We're going to divide by that number, and we're going to put plus c. And notice that I don't have the integral symbol anymore because I did the integration. Okay? Really common mistake is kids like to leave that integration symbol even after they integrate it. Don't do that. Okay, step 7, go ahead and do step 7. Step 7 was to replace the u with what u equals. So we get the x's back in the problem again. So you can write your answer like this, or you could put a 1/6 in front of the parentheses instead of putting a 6 on the bottom. Okay? So there's our answer. And something I didn't have you guys do is make sure at the beginning that this actually is a U-substitution problem. So we'll do that now. Do we have an inside function? Yes, we do. Do you see the derivative of that inside function? The derivative of 3x to the fifth is 15x to the fourth. So yes, we do. So yes, that is a U-substitution problem. Now some of you guys out there are pretty smart. And this might be like easy for you. You might be looking at this thing, I already see the answer. I don't need to do all those steps, Mr. Bailey. Follow the steps while it's easy, because you're going to have problems that are hard. And if you don't have the steps down by the time you get there, you're going to get lost. So please follow my steps, even if you feel like a smarty pants and you can do all this in your head. That's great. but still follow the steps. You'll appreciate it later. All right, so I want to give you guys an opportunity to try one now all on your own. So go ahead and do this problem right here, okay? Pause the video and do that problem from beginning to end. And when you unpause the video, you'll see the solution. Okay, so there's the final solution down there at the bottom. So if you didn't get that, you might want to study these steps here and see where you might have went wrong. But that is the basic idea for U-substitution. Now, since that's the basic idea, we're going to start delving into some other things that come up. And so the first thing we're going to be delving into is what I'm going to call extra constants. You'll see what I mean by that. You'll see what I mean by that. So, first of all, can we apply the chain rule? Well, I see an inside function, and what's the derivative of that inside function? It's 2x. Well, I don't see a 2x anywhere. I see an 8x. But believe it or not, that's actually okay. So I'll tell you why it's different. It's because there's an extra constant in there, and you'll see what I mean by that as we work. So, and then I'll tell you how, even though you don't see the derivative of the inside, you can know that it's still kind of there. It's just hidden. So, here we go. So, step 1, set the inside function equal to u. Step 2, find the derivative of this thing with respect to u. I'm sorry, with respect to x. Step 3, get the dx by itself. Now, I don't know if you guys have noticed this, but every time we get the dx by itself, every time this goes on the bottom and this goes on the other side, they just get switched, right? Pretty simple. Now, there's exceptions to that, but that is usually what ends up happening, right? But you'll see later on, we'll get to some problems where that doesn't happen. It's just because the algebra is different. All right, let's go ahead and move on over here now. So, step 4, we're going to do our substitution. So I'm going to replace that with u. The 8x is going to stay. And then I'm going to replace dx with du over 2x. Now, remember, so let's talk about now something kind of special here. So, what's the goal of U-substitution? Well, it's to make it look prettier. It's to make it look easier. It's to make it less confusing, right? And the way we do that is we get rid of all the x's and replace them with u's. So here's the thing. Even though, remember how I said at the beginning, I'll have an inside function, but this doesn't look like the derivative of the inside. Well, it's okay. Because what do I really want to go away? I really just want the x's to go away. It doesn't matter if the numbers go away. You'll see what I mean. So let's go ahead and work on this. For this, 8x and 2x. Well, they still cancel, right? The x here cancels the x here, and 2 goes into 8 4 times. And so if I simplify this, I end up with 4. I'm going to move it to the front. U to the 4th du. That's still an okay problem because the x's went away. So all that matters is that the x's go away. So now here's a new little rule of thumb for you. Okay, so what's the derivative of this? Well, it's 2x. I don't care about this. The point is, does this have an x and is this an x? If so, they're going to cancel, and that's all that really matters. So why did I call this problem an extra constant? Because when you're done, you're left with an extra constant in the front, but it doesn't matter that it's there because it doesn't change how we do the problem. Okay? It just makes it a little bit harder to recognize it as a chain rule problem. Anyway, so back to, let's review real quick. Set the inside equal to u, find the derivative, get the dx by itself, replace stuff, and everything cancels, but we're left with a constant, but that's okay. All right, so that's where we're at. Let's go ahead and do the next step, step 6, which is to integrate. So we're going to add 1 to the power and divide by that value, and we're going to put a plus c there. Don't forget at the end, to replace the u with what u equals. We're good to go. And there's our answer. Okay? And once again, yes, you could write this as 4/5 x squared plus 5, oh I forgot my power here, x squared plus 5 to the 5th power plus c. So either one of those are good answers. But there it is. So the only thing that's different here this time is that we don't really care about the constants, because constants don't matter when you're integrating. We need the x's to go away. So after you find the derivative, will the x's cancel? Okay? Now a really easy way to tell is look at the power here and look at the power here. This one should be 1 less than this one. And if that's the case, when you take the derivative, they're going to match. And then they'll cancel each other out. Alright, so let's go ahead and do one like that. So I'm going to have you guys do this one now. Just follow the steps. You should end up with an extra constant with this problem and see if you guys can get the final answer. So pause the video, give it a shot. When you unpause it, you'll see this worked out problem. Okay, there you guys go. So the main thing we'll focus on here for this is steps 4 and 5. After we do our U-substitution, we have a 6x down here and an 18x here. The x's go away, and 6 goes into 18 3 times, so we're left with a 3 in the front. And there's our extra constant. So sometimes you'll end up with some extra constants, but that's okay. What you should not have is any x's. Now you might be asking, well, what if there is an x left over? Well, for today, if you have an x left over, that means you did something wrong, because there shouldn't be anything left over. But there are problems actually where you could end up with an x left over, and there's a way to handle it, but we're not there today. They're very rare problems. They're really not all that important, but we'll look at them briefly. But for the most part, your x's should be going away. All right, so let's look at some other types of problems. For examples 3a and 3b, we're going to be looking at, and 3c actually. I don't think we need to do 3b. It's kind of repetitive, honestly. But we'll do 3a and 3c. For 3a and 3c, we're looking at what to do when you have weird-looking problems like this one, right? That's a little bit different looking because now we've got a fraction in there. And also what to do whenever we have square roots, or any kind of root for that matter. All right? So, well, the good news is the steps are pretty much the same, and so long as you remember your stuff from Unit 1, you probably won't run into any problems. So the steps are actually the same. Don't let the way that it looks at first freak you out. Just follow the steps. So what is step 1? Step 1 is to set the inside function equal to u. What's my inside function? Well, it's that. So step 1 is going to be to replace that. Or not replace it, but to make it equal to u. Step 2 is to take the derivative of that with respect to x. So far, nothing's different, right? Next step is to get dx by itself. The next step is to do the U-substitution. So we have 12x squared over, I'm going to replace that with u. I'm going to replace that with du over 3x squared. And what do you know? We have an x squared on the bottom and we have an x squared on the top. So they cancel each other out. No more x's. Everything's going pretty nice. Next, we can also simplify this. The 3 goes into the 12 4 times. So the first hurdle to get over here is to not let it freak you out. It's really no different at all. So for the whole process of U-substitution, these types of problems don't matter at all. They just look scarier. But now here's the next hurdle. It's not only to let the looks not freak you out, because you can still get to step 5 rather easily. But the next hurdle is integration. So do you remember how to deal with this situation when you have a u or a variable on the bottom? What did we do about that back in Unit 1? Or actually back at the beginning of Unit 2? Well, what we did was we moved it to the top. And we changed the exponent's sign. Right? We just rewrote it. And now we can integrate it like we're used to, right? So we add 1 to the power. If you add 1 to a -4, be careful. it's negative 3. And then we divide by that number. All right, so now we have 4, negative 3, over negative 3. And we're going to replace the u with what u equals. X cubed minus 4. Okay, now here's the third and last hurdle. So the first hurdle is don't get freaked out. It doesn't change the first 5 steps when it looks like this. The next hurdle is remember how to integrate it when there's a variable in the bottom. The last hurdle is rewriting your problem. So as we already talked about, you could write your problem like this is fine. There's nothing wrong with this answer, but I want you guys to know you can also write it like this, right? But there's actually another way to write it now. Since we have a negative exponent, a third way that this problem can be written would be like this. Instead of having the x cubed minus 4 to the negative 3 power in the numerator, you could put it in the denominator with a positive 3. I don't remember which one my software that I use to generate your questions is most likely to do. I don't believe it would do this one. It could do this one, but I think it would probably do this one. Okay, so when you have a negative exponent, I would just make sure you know how to write it in all 3 ways just to be safe, but there it is. So not a whole lot changes there. And you run into a similar issue whenever you have radicals. So let's take a look at example 3C. I'm going to skip 3B. It's honestly just the same thing as 3A. It's just easier because it's already written as a negative exponent. So we'll skip 3B. All right. So let's do this one. All right, so step 1. What's the inside function? Well, in this case, instead of identifying the inside function by looking what's inside parentheses, we're identifying what's the inside function by what's under the radical. So in this case, my inside function is 2x to the 4th plus 1. Okay? Next, we're going to find the derivative of that with respect to x. Step 3, get the dx by itself. Step 4, let's do some U-Substitution. So I'm going to replace what's under the radical with a u, and I'm going to replace the dx with du over 8x cubed. And the x cubes go away, and 8 goes into 32 4 times. So I'm left with a constant, but that's okay. It's okay to have extra constants left over. Just don't want any x's, right? So there you go. Pretty nice. So once again, even though it looked weird because of the square root in there, steps 1 through 5 were completely the same. So the new thing called U-Substitution doesn't change at all, regardless of whether it's written as a fraction or a radical or just a basic problem. Same steps every time. But now we do have to remember how to do this. So in case you guys forgot, when you have a square root, this is a second root when it's a square root, and the power if it's not written as 1. And so what we did for this is just like with the fraction one, we rewrote this, right? Instead of having it 4 square root of u, we rewrote it as 4u to the 1/2 power. And that way we're set up so that we can do our power rule for integration. So that's mainly the difference there. Okay, so don't get freaked out. Steps are all the same, and don't forget how to integrate with radicals. Okay, so how do we deal with this now? We add 1 to the power. We talked a little while back about how to do that. If you want to add 1, what you do is you add the top and bottom together. So 1 plus 2 is 3, but you keep the same denominator, so 3/2. And we're going to divide by that number. Now, I'm going to write this, but don't write it, because we talked about this. Instead of dividing by 3/2, what did we say to do instead? It's really inconvenient to divide by a fraction. So instead of dividing by the fraction, what did we say to do? We said to multiply by the reciprocal. Okay? Don't forget your plus c. So there's our integration. So add 1 to the power, and since it's a fraction, multiply by the reciprocal instead of divide by the fraction. All right, so for this one, we're going to need to simplify it a little bit more first. Let's go ahead and put the 4 with the 2 there. So we're going to get 8/3. And then we need to replace the u. So we have 8/3 and then 2x to the 4th plus 1 to the 3/2 power now plus c. Okay? And there it is. I don't think that, I'm pretty sure my software is not going to write this any other way than that right there. So you're safe on that one. You don't have to worry about it. There's pretty much, I mean, of course, the fraction thing could still apply that we talked about earlier. So for instance, you could have an 8 here and a 3 down here. I think that's possible. I'm pretty sure, though, that they would stick with this method. But either way, it doesn't matter. Okay, so how do you deal with square roots, or any root for that matter, and fractions? Well, pretty much what steps 1 through 5, the new stuff for today, doesn't change. You just have to remember how to integrate with those types of things. So you guys aren't going to do A1. It's not necessary. It's just repetitive. But I'm going to ask you guys to do numbers 2 and 3. So pause the video and try both of those problems and see what you guys get. Okay, so there's your solutions for 2 and 3 there. So on number 2, the thing that I would draw your attention to is this step where we rewrite the 5/u⁵ to be this, so we can do our power rule. The other thing I draw your attention to is that since I had a negative power here, instead of leaving it on the top with a negative power, I put it on the bottom instead with a positive power. Okay. As for this next one, once again, I would draw your attention to this step where we change the square root of u into a u⁵. And so when we do our integration, we add 1 to half to get 3/2. And instead of dividing by 3/2, we multiply by the reciprocal, which is 2/3, which when you do 2/3 times 5 gives you 10/3. And then replacing the u with what u equals, we end up with the expression you see there. So there you guys have it. That's U-substitution. So let's review really quick before we call it quits. What is U-substitution? Well, U-substitution is a way to make a really ugly expression look nicer. And when can you do it? When you have an inside function and its derivative, or something where the derivative x's will match to cancel each other out. Okay? It's the opposite of the chain rule. So that is what we learned today. Here are the steps that I said were included in your notes. You guys have them. These steps are probably written a little bit different than the ones I gave you. They're the same steps, just kind of maybe like written differently. But either way, use whatever steps you prefer. You'll notice there's a blank on number 6, and that's because we are going to do something later on. Earlier we talked about how, well, what do you do when there's an x left over? If you did everything right and there's still an x, well, that's what step 6 is for. We're going to talk about how to handle that situation. But it's not really all that important because honestly it doesn't happen very often. Usually these other steps get you there. So that's the end of our lesson, and we'll see you guys later.